go again. Now a review of the oxygen hemoglobin saturation curve, a gross oversimplification of the factors that might be involved with it, but a way of sort of seeing what's going on, easily seeing what's going on. Here's the storyline. If we have a graph showing the concentration of oxygen that's being loaded onto hemoglobin versus the partial pressure of oxygen, we would see that at 0 partial pressure of oxygen, there would be 0 loading. Generally, you might expect to see a kind of a diagonal line right here. As the partial pressure increases, you expect more oxygen to be loaded onto the hemoglobin. And that is true to an extent. There's a rapid loading and then it tapers off. Now, what we're concerned right here about is this idea about a left shift and a right shift. Now, this is the so-called normal saturation curve. But in a left shift, what happens is we're talking about a situation where the hemoglobin is loading faster, and in the right shift where it's unloading. Well, this right here would represent what's going on in the pulmonary circuit, where there's good conditions. These good conditions would be in an area where there is high oxygen, high pH, low hydrogen ion concentration, low carbon dioxide concentration, and a relatively lower temperature. This would represent what's going on in an area, say near a busy cell, where there is low oxygen, low pH, high hydrogen ion concentration, high carbon dioxide level, and a higher temperature. So the graph itself is meant to represent the conditions that cause the faster loading of the oxygen and the conditions that cause the faster unloading of the oxygen. And again, it's generally referred to as a left shift when you can load better, faster, and a right shift when you unload better, faster.